Next, we're going on to the dynamic multiple model estimator, where the system mode is going to undergo switching in time according to our model. So the way we model the system is that the state at time k is a transition matrix F, which depends on the current mode at time k times the previous state x at k minus 1 plus process noise for time k minus 1, which now depends on the current mode k. And the output zk, the measurement, is a function h of the mode, mod mk, times xk plus w, the measurement noise at time k, which is again a function of the mode. Now here mk denotes the mode or model at time k, really is the one in effect during the sampling period ending at k. This is why this is k, this is k, this is k, this is k again. Such systems are also called jump linear systems, and our mode jump process is assumed to be left continuous, i.e. the impact of the new model starts at tk plus or at tk minus 1 plus and goes on until tk, and this is the same model or mode is a constant during a sampling interval, which starts at tk minus 1 plus and ends exactly at tk, and this is why we have an mk here and we have an mk here. Now the mode again is assumed to be one of our possible modes, so m of k now, its time varying, is one of these r j from 1 to r possible models. And in terms of terminology, it's important to point out that the continuous valued vector xk is called base state, and the mode k, the discrete variable mk, is called the model state. So we have a base state and a model state. And another point to bring up is, in this case, the entire state of the system would consist of xk and mk, so it is a hybrid state, and this is why it's called a hybrid system. As an example of what this modeling tool can accomplish is we can have the transition matrix for a certain model being equal to fj, the process noise index k minus 1, that's from time k minus 1 to time k really, for model number j could be Gaussian distributed with some mean uj and some covariance qj, so we can have a lot of flexibility. And as a matter of fact, the structure of the system, as you can see from fj being a different matrix, can be different from model to model, and even the dimension of the base state vector can be different from model to model. Some compatibility is required, as we'll see later. But typically one state vector should be a state subset or subset of another vector. And the mean uj can model a maneuver as a deterministic input. So we have quite a few options here. Now, the Earth mode history or sequence of models through time k is denoted by m super k l. So this is through time k sequence number L, which starts with model I1, I sub 1 at time 1, and ends with model I sub k in this sequence at time k is model sub ik in this sequence R. So there's a second indexing here, R, and the big thing is that R, the number of possible such sequences by time k is r to the k. So I sub kr is the model index at time I sub kappa L is the model index at time kappa from history L, or sequence number L. So I kappa L is between 1 and R for kappa going from 1 to k, namely at all time. So again, here you see that R to the k, that's the big problem with this approach, would increase exponentially with time. For example, if you have two models and you have only two sampling times, you already have 2 to the 2, that's 4 possible sequences of histories. It can be 1, 1, 1, 2, 2, 1, or 2, 2. Now, we need a mathematical model for the mode or model switching. Namely, that's a jump process, and this will be assumed to obey a Markov chain, which is a special case of Markov process with a discrete, in a discrete space, with known transition probabilities. Pij will be the probability that the mode at time k is mode j, given the mode at time k minus 1 is mode I. So this is the jump from I to j, and again these jumps occur at the end or right after a sampling time. Now, these mode transition probabilities will be assumed time invariant and independent of the base state. This is yielding what is called the homogeneous Markov chain. Our system, described by these equations 1, 2, and 8, is a generalized version of a hidden Markov model. In the literature, there's a lot about hidden Markov models, like in speech processing, speech generation. They have been used very successfully. But ours is really a hybrid version in which you make incomplete, imperfect observations. So hybrid has a continuous state, has a the base state, and has a model state, and you make imperfect observations only on the base state. The typical hidden Markov models are only discrete, and you make observations on the discrete state. Again, imperfect, but ours is more general. The event that model J is in effect at time k will be denoted in a concise manner as M sub j at time k, denoting that the event that the model at time k is M sub j. And we will look, in view of the fact that histories is what really matters in this jumping mode situation, the conditional probability of the Lth history mu super kl as the probability of M super kl given Z super k. So this will be evaluated next using, again, Bayes' formula. So this Lth sequence of models will be written as, so M super kl as M super k minus 1s and mj at k. So we have the parent sequence of this mkl as mk minus 1s. Its last element is mjk. So sequence number s through time k minus 1 is the past history, the past or the parent in this longer sequence through time k. The last element of this is number j at time k. Now, in view of the Markov property, the probability of having model number j in effect at time k, given the entire past sequence, M super k minus 1 s, so sequence number s through time k minus 1, really equals to only the probability conditioned only on mi k minus 1, where I is the index of the last model in the parent sequence S through k minus 1. So what we have here is the Markov property given all the past. The probability condition on the entire past depends on the last element or the last model within the past sequence. And this is the Pij defined earlier, the jump probability. Now, the conditional PDF of the state, really the base state at time k, is obtained using the total probability theorem with respect to the mutually exclusive and exhaustive set of events that we have the sequences MKL as a Gaussian mixture but with an exponentially increasing number of terms. So the PDF of the base state xk given the total set of measurements up to and including time k will be the sum of the PDFs P of xk given sequence number L through time k and the set of observations through time k times the probability of this sequence number L through time k given the entire set of data z super k, and this is to be summed L from 1 to r to the power k. So what we have is a simple use of the total probability theorem where we defined a set of mutually exclusive and exhaustive set of events. And these are the MKL because they're all different and they encompass or cover all the possibilities. Therefore, we can see that to each mode sequence we will have to match a filter. And we will have an exponentially increasing number of filters that are needed to estimate the base state, which makes this approach, which is optimal, but it is impractical. Now, one thing that we should quickly go over is how to come up with the recursion for the probability of a mode history using base formula. Mu super KL, that's the probability of sequence number L through time k of modes, given the entire data, z super k, can be rewritten as probability of the same sequence, given the latest piece of data and the previous data set. And as usual, we'll do switching with base formula between this MKL and the latest piece of data. This will be then P of Z of at K given the sequence number L through time K and the past data times the probability of this sequence through time K, sequence number L, given the past data. This will be kept as is because this is the likelihood function at time k of the sequence number L. The second term will be decomposed. The MKL really is the joint event that at time k we have sequence number j, that's the last element of this sequence. This is the parent sequence M super k minus 1s. So this is equal to these two events. Now we can rewrite this probability mjk given mk minus 1s and zk minus 1. So this is using the equation that probability of A and B is probability of A given B times probability of B. There's a common conditioning here, and the event B is this sequence mk minus 1s. So what we have here is the probability of the sequence mk minus 1s given zk minus 1, which is denoted according to the previously introduced notation as mu super k minus 1 and s. So one more simplification can be done is what we have here. Once you know the modes here, the past measurements don't matter because the jump probabilities are independent of the base state. So this conditioning can be eliminated, and we have here PMJK given the previous, the parent sequence. And really, as indicated before, from the parent sequence, all we need is the last element. Now, if the current mode depends only on the previous one, as indicated before, it is a Markov chain, then what we have is the updated probability of sequence number error through time k is this normalization constant dividing the whole expression times the likelihood function of this sequence at time k, so that's p of the measurement at time k given the sequence of modes and the past observations, times the probability of the last mode in this sequence given only the previous mode in this sequence. So the last element of the parent sequence, that's MIK minus 1, and the probability of the parent sequence. Now written in a very compact manner, mu kr is 1 over c, normalization constant, likelihood function, times jump probability times parent sequence probability. So I is sk minus 1, the last model of the parent sequence S. So what we see here is in this approach we have to condition on the entire past history. Our parameters are Markov. The problem, the reason this has to be done is that what we have, the joint state and base state and model state are handled here separately. They should really be handled simultaneously, which makes the problem more complicated, but the only feasible way of implementing it is using mode sequences, mode condition filters, but then we run into the problem of the exploding, exponentially increasing number of such filters. So we need some suboptimal techniques. We need practical algorithms. Suboptimal techniques. One simple technique would be keep the n histories with the large probabilities, discard the rest, and renormalize the probabilities such that they sum up to unity. That's one possibility. Another possibility, instead of discarding histories, merge them, combine them. And this approach leads to the so-called generalized pseudo-Bayesian techniques, which combine histories of models that differ in order models. The so-called first-order GPB, denoted as GPB1, considers only the possible models at the last sampling period. Everything before that is lumped. There's a GPB2, the second-order version, considers all the possible models in the last two sampling periods, and the first one will require R filters, because we have R models now and all the past is lumped. The second is R square filters that will have to operate in parallel. Now, there is another algorithm, the so-called interacting multiple model estimation algorithm, which it turns out does something smart and ends up to be similar to GPB2, but has the cost of GPB1, and that's one of the few cases where you get quite a bit for very little. It's not something for nothing, but quite a bit. Now, it was mentioned up to now that the mode transition probabilities are assumed known. Really, they are not known. Nobody will give them to you. The filter designer has to select them. So these are really estimator design parameters that have to be selected in the design process of the algorithm, similarly to, say, the selection of the process noise variances in the motion equations. In the dynamic equation, typically those are not given. They model what we don't know, the process noise, and here the jump probabilities or mode transition probabilities will be used to model again something we don't know by a Markov process, namely what is the probability that the mode changes from one time to another. This will be discussed in more detail when we illustrate how the design of an actual system can be carried out with this algorithm. Now, next is we will go to the interacting multiple model, the IMM estimator, which operates as follows. At time k, we compute the state estimate under each possible current model. We use R filters, but each filter we will use a different condition, initial condition, as a combination of the previous outputs of this filter. So we use a so-called mixed initial condition. The filters exchange information just before the beginning of the cycle based on the previous estimates, and they do their own thing, come up with their own estimates, and again, next cycle will exchange information. So the way we do this is we use the total probability theorem as follows. The PDF of the base state xk, given z super k, all the data up to k, is decomposed with respect to the mutually exclusive and exhaustive set of the current models only. So this is a sum of a fixed number of terms r at every k. And we have to figure out how to calculate these things in a nice manner, obviously. So this is the PDF of x given model number j, the current measurement, the latest measurement, and the past measurements, times the probability of that model being in effect at time k. The way we calculate this is as follows now. The PDF of the state, given the model being number j at time k, and the measurement, and the past data, is the PDF of the measurement. So we switch Wood-based formula between z and x. So z is here, x is here. Once x is here, there is no need for the past measurements because z is determined by the model and the x. So this is the likelihood function, but it has x in it, times the probability density of x given the current model and the past data. So this will be the initialization of the filter in cycle k, and this will be the update with the likelihood function of the state probability density function. And here we have just a normalizing constant. Now, the last term, the prior, this is the way we initialize. How do we initialize the filter in a cycle? P of xk, density of base state at time k, given that the model at time k is number j, and the past measurements, do one more decomposition with respect to the previous models, mi at k minus 1, I going from 1 to r. So what we need here is PDF of x, given the current model and the previous data, times the probability that at k minus 1 the model was I, and that given that at k the model is j, so, and the past data. So this is like a one step back inference. Now this is approximated as the PDF of the base state x, given the model mjk, given the previous model mik minus 1, and the entire past data now is approximated by the outputs of the mode matched filters at time k minus 1. So this is output for mode L at time k minus 1, state estimate and covariance. And we have R such outputs. times the probability that if now my mode is j, the previous time I had mode I. So m I given j, which is now written if I know that previous time I had mode number I, the only term here that matters is for number I, with index L equal I. So this is sum P of xk given the current mode mj, the previous mode mi, the previous estimates coming from the filter match to this mode mi, and this probability that now if I have mode j, previous time I had mode I. So the input to the filter match to mode j follows from the interaction of the other R filters, which results in a mixing of those estimates x hat I, k minus 1, with weighting probabilities mij, mu ij, called, these are the mixing probabilities. So what we have here is mixing probabilities, and this is how the estimate based on the past data will be calculated. This really amounts to hypothesis merging at the beginning of each estimation cycle, as indicated by Blom, who was the originator of this IMM estimator. More specifically, we have R hypothesis at the beginning, that in the GPB2 they fan out into R square and then they are mixed into R. So what we have is we keep them R. So it is a simplified version, substantially simpler version as GPB2. Nevertheless, performance-wise, it is very similar, it turns out. So what we have, and we'll start for the description of one cycle, is there is a filter matched to mode M1, a filter matched to mode M2. You get a measurement. Would an initial condition for this filter match to mode 1 x super 0 1 and the initial condition x super 0 2, we initialize at the beginning of the cycle each filter, and they put out mode condition estimates for the end of the cycle, x hat 1 kk, x hat 2 kk. Each puts out a likelihood function. These likelihood functions go into the mode probability update and mixing probability calculation. Two probabilities are needed here. One is this mu kk that is used the previous time here to mix the initial conditions. This and this from the previous time are here. X hat 1, k minus 1, k minus 1, x hat 2, k minus 1, k minus 1. These are shared by the two filters using these one-step back inference probabilities. With this, we have a full description of how the filter operates, at least in principle. The equations will be shown later in the textbook in more detail. So what we have now is use of the mixing probabilities. It turns out the same likelihood functions are needed for the mixing probabilities as well as for the final mode probabilities. And the mode probabilities, together with the latest mode condition state estimates and their covariances, are used here to provide for the output the combined state estimates across the modes. And these equations are the standard mixture equations. So this is an output only. The filter operates on the mode condition estimates. You can see you have two estimates, R for R models, and the previous two estimates or R estimates are here. They are apportioned to each filter. So you have R estimates, R filters, R estimates. Then finally, there's one estimate for the purpose of output. And here are the details of the algorithm. First is the calculation of the mixing probabilities. Mu ij k minus 1, k minus 1 is the probability that at k minus 1 I had model number I, if now at k I have model number j. So that's the one step back inference, and this is given the past data only, namely before I get the latest measurement. Again, with base formula, we switch between mj and mi here, so it's a p of mj given mi, zk minus 1, p mi k minus 1 given zk minus 1. But notice here, because this is Markov, this doesn't matter. So this is a mu ij. Sorry, this is a pij. This is a pij jump probability, and this is a mu I. So what I have here is a pij, the jump probability, from I to j, times the probability that I had number I before. So this is the mu I given j. And this is the expression of the normalizing constant. The mixing with these mu I given j probabilities is just a combination of the previous state estimates. That's the standard mixture equations we have seen already a number of times. And the covariance will be, again, a mix of the covariances plus a spread of the means term. Here we have x hat super j, that's the weighted version, the average of all these mode conditioned estimates here, and these are the individual mode conditioned estimates, sum I1. So this is the outer product, spread of the means, plus the covariance in each case, or summed up over all the possible modes. The mode matched filtering is done according to standard Kalman filter, so equations are not repeated here. What's important is what comes out from each filter, the likelihood function, and this is why when we discussed earlier the Kalman filter, it was already indicated that the likelihood function of a model or of a filter matched to a certain model is at time k, the PDF of that measurement given the model and given the past data. So this is what will be used to figure out in a probabilistic sense which of the model is the current one, which of the possible models is currently in effect. So this lambda j, which is the PDF of the current measurement, will be calculated as a Gaussian. Argument is z. This is the predicted measurement based on the model on the filter for model j, predicted to k, from time k minus 1, and starting from the initial condition received from the mixing. And there is an innovation associated with this. This is the covariance of the filter number j's innovation. S super j at time k, again, this starts from the covariance received from the mixing. This is the likelihood function for model j at time k. The mode probability update, mu jk, which is the probability of having model number j at time k given all the data through time k, is again by decomposing z super k into little z at k and z super k minus 1 and using base formula to switch between zk and mjk, we end up with this is the likelihood function at time j, lambda jk, and this is the probability of mode j being in effect at time k given the past data, which is the sum. We do a total probability theorem application, decomposition here, with respect to mi k minus 1 for all the possible modes at time k minus 1. So I goes from 1 to r. Put here in the conditioning, and write the probability of this event given the common conditioning zk minus 1 prior to time k. But this will be pmj given mik minus 1, and this is irrelevant, the past measurement, because it's Markov. This is a p from I to j, a jump probability from I to j, pij, and this is the probability of having model number I at time k minus 1, so mu I k minus 1. This is the way we update the mode probabilities, and we have a normalizing constant again such that everything sums up to 1, and it turns out that in the mode probabilities the normalizing constant relates to that one step back inference, the mixing probability normalizing constant according to this equation. So really the two are related, and calculating one helps evaluate the other one already. Finally, for the purpose of output, we combine the estimates from the mode conditioned filters and the covariances using again the standard mixture equations. X hat is sum of x hat j mu j, everything with argument k, and the p is sum of mu pj, the mode conditioned covariances, plus a spread of the means, where this x here is already the combined mean. These are the individual filter outputs. And again, this combination is really not part of the recursions going on inside the algorithm, but it is for the purpose of a concise presentation of the output. Let's look at the first example with the IMM estimator. This is an academic example, then we'll go to a realistic one. This deals with the motion of an object turning 90 degrees over 20 sampling periods. It's a relatively benign motion. And we looked at 2 IMM in this case. We'll consider an IMM2 using 2 models, and then an IMM3, an IMM with 3 models. The 2 model based IMM uses a constant velocity model, second order with no process noise, so it's a constant velocity, zero acceleration model. And the third one is a Wiener process acceleration model with process noise, which is the acceleration increment over a sampling period, as we discussed earlier, and has this process noise variance 10 to the minus 3, which if you write it as a standard deviation is 0.03 meter per second square. So that's the acceleration increment. It turns out that the acceleration, this was chosen as a good number, and because the results were good, and you go back and compare this with the actual acceleration, which is 0.075, really acceleration in this case corresponds to a little bit over 2 standard deviation of the noise. So what we have in this case is a very close relationship between the selected process noise. It's about half of the actual acceleration of the object. Now, the Markov chain transition matrix was taken as, and this is a design parameter. In this case, we assume that from one sample to the next, there is a probability of 95% that the object, if it does not maneuver, it will continue not maneuvering. It has a 5% probability of starting a maneuver. If the object is maneuvering, has a 95% of continuing to do the same thing, and a 5% of getting out of it. What's important is that these numbers, which are never going to be given in the real world by anybody to a designer, have to be selected by the designer. Fortunately, the final results are not very sensitive. We can take a P11, that's the first term, between 0.8 and 0.98, and not see tremendous differences. There will be some. The lower value will yield a lower peak error during maneuver, and the higher value will yield more peak error during a maneuver. So what we have is if this is a lower value, means there's a higher probability that a maneuver starts. The filter will be more alert to a maneuver starting. So lessening this, we increase this because the sum across the rows has to be unity, and therefore it will catch a maneuver better. If this is higher, P11, then P12 is lower, the filter believes it's less likely to have a maneuver. Therefore, if a maneuver does start, we'll have a peak error during the maneuver, at the beginning at least, higher. So, a high number here is a low bandwidth filter, and the number in P12, if it is higher, gives us a higher bandwidth filter. The second option was an IMM with 3 models, using the previous 2 plus a third model, which is a constant acceleration, third order model without process noise. This was selected because the model was actually a constant. The simulated truth was a constant acceleration. So in this case, the Markov chain transition matrix was, this is probability if it doesn't maneuver, it continues doing so. This jump from 1 to 2, it starts a maneuver, has an acceleration jump. The second model is starts or ends a maneuver. This third model, it continues the maneuver with constant acceleration. Here it gets out of it by going back to model number 2. So there was jump from 1 back to staying at 1, jumping from 1 to 2. If it's in 2, can go back to 1 or can go on to 3. If it is in 3, can continue doing the same thing or go back to 2 and then possibly back to 1. Here are the results of position root mean square error for the 2 designs, and you can see that there is not a major difference between the 2. The IMM3 has slightly lower error here, the IMM2 has a slightly lower peak error. The peak errors are approximately equal to the measurement noise standard deviation. In this case, the measurement noise standard deviation is 100 meters, and this was a lot smaller than 2 other competing algorithms which we don't discuss here, the input estimation and variable state dimension. What we have here is the non-accelerating or quiescent period. The errors are somewhat larger, but we have an RMS noise reduction factor of 2. Because what we have is, this is in a coordinate, RMS is around from 100 meter measurement noise standard deviation in each coordinate. This was assuming position measurements directly in X and Y. It's down to about 50, so that's RMS factor of 2, mean square reduction factor of 4, which is pretty good. So the variance noise reduction of 4. For velocity, again, they were fairly close, not much of a difference between the 2. And maneuvering mode probability, you can see that the 2 model IMM was kind of hovering and not knowing whether there is something or nothing. When there was nothing going on, it figures out that something is going on with about 70% probability. On the other hand, the IMM3 was a little bit better. When nothing was happening, it was attaching 25% probability to the maneuvering mode. But when it was, which is good because it should have been very low, when it does maneuver, it ends up with 75% probability, which is good because then it happens. So you can see that the IMM3 seems to be somewhat better in recognizing what's happening in this case.